Hello, can you hear me? David?
Yes, can you start to record?
Yeah, I will definitely. Is it live?
Yes.
Okay, so how many attendees are here today? Only four? Did they understand the timing which I gave? Or they still thinking five? The Not five actually. There will be around seven. They are thinking about seven maybe.
Maybe they joined before.
Mhm.
After. Sorry. Okay.
Yeah, after. So how about that the guy from Peru, Marcio? He's also not here today. Otherwise, he's pretty regular. So okay, what did we study in the last lecture? Who knows?
I'm Nargis Gafoor. We studied about resonator cavity. Then we different kinds like cofocal, spherical plane cavity, cofocal resonator cavity, spherical plane cavity, and then laser modes, standing waves. These were the things that we discussed.
Okay, one of the important things which we discussed in the last lecture was the longitudinal modes or axial modes. Okay, so the resonator cavity lecture was before that actually. And so the cavity optics and longitudinal modes. And what is so special with the longitudinal modes that in case of normal laser, it has to be controlled. But in case of ultrafast laser, sorry, I messed up something. In case of a normal laser, these axial modes are supposed to be removed actually, only one or two or something. And in case of ultrafast laser, we need these modes. And now today we are going to study other kind of modes. Let me share my screen with you. So you can see something on this, David. You can see or not? Please continue.
Yes, we can see.
Okay, so what do you see here? These are other kind of modes, and especially on the right side of the screen. That is, we call it transverse electromagnetic modes actually. And today we are going to study these modes and see what these modes are. Okay, so transverse electromagnetic modes, or in short, we call it TEM. Okay. And these modes actually are dependent on the cross-sectional dimension of the cavity. So dimension of the cavity mean, I mean, if you remember in the last lecture, what we studied, that word longitudinal modes. So longitudinal modes, basically, it depends upon the length of the cavity. So length of the cavity, or which is also called axial modes, okay, along the axis of the cavity. So the longitudinal modes are very important. The transverse modes are somehow, it's troublesome. And we are supposed to control these modes in any kind of laser. So it depends on the dimension of the cavity. What is the length, what is width, height, etc. If you see in these diagrams here, just a minute. Okay. So here, this side, let me see. Okay, so on this side, okay. So this is the direction, it's a longitudinal direction, okay. And cross-sectional dimension mean longitudinal and width and height as well, okay. So in case of a longitudinal, we know that there are different kind of frequencies are existing in the cavity, okay, like this and this, like this and this and this, okay. But here, if you see in this diagram, this kind of wavy pattern also exists, but in transverse direction, okay. It's not in a longitudinal direction, but transverse direction. So, and on the left side, you see that the animated stuff. And if you see here, and this one, first case, second case, third case, these are all transverse modes, okay? And so on, okay? It looked like in a box, different levels, energy levels in a box. Okay, so if the cavity dimension is big enough, then we may have all these modes. Along with the longitudinal modes, we have transverse modes as well, okay? So what does it mean? Like you have these longitudinal modes here, and we have like this as well, okay? Here, here, and here as well, okay? So these transverse modes actually, as it depends on the cross-sectional dimension, and these cross-sectional dimensions we can control with certain methods or something. So we can control these modes somehow. So if you see in this figure, you can also see that there is trough here. Okay, so these are black and white, black and white, and black and white. It depends on the the modes, how many modes are there, and something like this. In the next slide, probably you can understand more. Okay. If we have a cavity, okay, and if we use a kind of concave lens, or it's also called negative lens because it's a expand your beam when it passes through, and we focus it on somewhere, we can see these TEM modes. Okay, so like here, you can read like, okay, so kind of patches, black patches, black, white, black, white, black, white. Okay, and show you here these. So what here, these kind of patches you can see on a screen or something like this. So if you see these kind of patches, if you expand the laser beam, on a, like using kind of convex lens or negative lens, and see on the screen, you can see these kind of patches. If in the cavity, if these modes are existing, okay. In short, actually, what is called, it's called TEM, okay, and along with TEM, we use M and these are two integers, okay. How to represent these modes, okay. So TEM modes is electromagnetic modes, so it has to be represented in a certain way. It's not like a longitudinal mode, okay. M and N, these are any kind of integers, and they will represent the intensity minima, okay. Like if it is, for example, TEM 00, this is the most ideal mode, okay. It's the simplest, smooth, and it's like very nice Gaussian kind of shape the spectrum will have if the cavity is having only this modes, okay. If we have like this, TEM 01, okay, so TEM 01 or TEM 10, okay. So what it will show the two patches, single minima dividing the beam into two bright spots, okay. So like this one here. This one is TEM 00 mode, and this one is TEM 01 mode. And if it is 10, then it can be written like, and it appears like this. Okay, so there can be like a 01, 10, 12, 21, 22, something like this. Okay, so like here, if it is 11, so what beam will have? It has two perpendicular minima dividing the beam into 4 quadrants. Okay, the 4 patches. So 4 quadrant means that it will be like this, like this, like this, like this. It's not in this these figures here. Okay, so like this. This is 1, 1, 0, 1, 1, 1, and then after that it can be a 2, 2, 1, 2, and if you have like 2, 2, so you can see that 1, 2, 3, 4, 5. These are almost 9 patches there. And why these are? These are because of this thing. what you see here. This one, 0, 0. This one, 0, 1. And then you go on further, 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 and further. Okay. So these bright spots you see because of these, you can see the wavy patterns in the cavity. Okay, so first thing is that it is represented with the TEM, TEM, and there are two integers, M and N, which shows that, I mean, how many patches are there, how many minima are there. Okay, so if you have this, if you can see this point here, the patches, they are separated with some kind of interval, and these intervals is called nodal lines. So what is nodal lines here? Like if this one, this line is separating the two patches, it's called nodal lines, okay? And third point here, if you see, transverse modes, actually, what do? They characterize the intensity distribution, okay, across the cross-section of the laser beam. In other words, like what you see these waves here.
In the second line, okay.
Yes, which second line?
In the second point, patches reverse ho the patches become reversed in the med. So how it's happen?
If you see this diagram below here, this one, okay. So
okay,
how the phase reverses here, you can see. Crust become the trough become the crust. Okay.
It's become in the negative region.
Yeah. Yes.
Okay, sir.
Okay. Okay. So third point.
Excuse me, sir.
Yes.
Sir, when you tell us about the TEM mode, it has two integers. I think they represent the theta and r direction of the cylinder, and z direction is missing, which means it's transverse mode. That's why z is missing.
Z? I didn't get your point. Say it again.
In the TEM mode, just like TEM01 mode,
yes,
in which it tells us that it has one minima in r direction. It's actually the cylindrical coordinate, theta, r, and z, m, n, and the third one is the z. Actually, I have worked with these transverse modes, and it has three integers. First one is theta, second one is r.
Yeah, that if you want to that detail, I mean theoretical detail, it's not necessary here. Here I just want to show that these are the integers, okay? And how does it look like actually? That is, you are right on your side actually. If you go in depth, actually, this is in the electromagnetic theory. You can read all these things. Okay. Okay, so how do you actually see? You can see this on the left side, these modes, if you are able to magnify your beam coming from the cavity. Okay, so most of the cavities or most of the laser in the market, what you see, they come with the TEM00 mode. Okay, and simplest mode, and you have one spectrum here. If the modes are increasing, then you have number of lobes like this. It's possible. Output spectrum will be like this, which is not needed. Okay. So in this case, what we need to do, the purpose of these modes, to study these modes a little bit, not in detail, that we need to have a proper output beam, okay, proper output beam. And for this one, we need to have a TEM00 mode. Okay. We don't need to have 100, 122, whatever it is. We need to have a TEM00 mode. If we have higher modes, it's possible that we can have higher energy at the output of the cavity. But the beam is not Gaussian. I mean, it will have like number of humps, which is not needed. So that is why these modes are existing, okay? And both longitudinal and transverse mode, both are existing. We cannot eliminate them 100%, but we try to minimize the presence of these modes to control, in other words, to control these modes. Here, what do you see here? These transverse modes are existing because of the dimension of the cavity. So the dimension of the cavity is length, height, width, etc. So how about if we use any kind of aperture or any kind of iris, so that if it is possible for us to make the beam to pass through this kind of aperture, can we control the transverse modes in this case? Yes. Okay. So if you see here, this is the normal case. Okay. When the cavity is there, the mirrors are there. Okay. All the light passes through the medium. Okay. And we have number of modes. Okay. This is 10, 10, 10 or 01 modes. So in this case, at the output, you will see the spectrum. Okay. So what is the spectrum actually? Spectrum, you have on the one side, you have wavelength or frequency. On the other side, you have intensity. Okay. This spectrum, to take the spectrum, to make measure the spectrum is very important in the laser. So if you have this mode, then your output spectrum will be like this. And if you have like this, then it will be like this. Okay. Which definitely, it's not an ideal case, but in this case, you may have higher energy, but the beam profile will not be perfect. And if you go down here, we use here kind of aperture. Okay, we stop the beam inside the cavity, not outside the cavity, inside the cavity. We make it possible to pass through this aperture. So when it pass through this aperture and oscillate between the two mirrors of the cavity, at the output we get nice beam and TEM mode. Okay, but there is a give and take. You know that most of the medium is not filled here. Okay, so we only utilizing this center portion of the laser medium. So it's obvious that in this case, the energy of the overall energy will be reduced, but you have fine beam. In some cases, especially in case of military and defense applications, where the beam profile is not important, but energy is important. In that case, these modes, how many modes are existing, it doesn't matter. Okay, energy matter. So how many modes are there doesn't matter. So it has energy then to use whatever. You don't need to use aperture or any kind of things. But when you do some scientific experiment or some precise applications where your beam has to be very nice and smooth, then in this case, you need to use aperture so that you can have very nice beam. Okay, so in this scheme, you can see if you don't have this one, your beam will be like this outside here up to here. And if you have this aperture, then you have output here. Okay, so same thing which I mentioned here. CAM 00 mode actually is supposed to be like, it's called a uniphase mode. And in this case, the spatial coherence is very high. Okay, and as I mentioned, that it can be used in a very kind of very precise kind of applications. So these applications are like to make it to focus the beam on a small spot, which is not possible if you have the higher modes. Okay, and as I mentioned, that higher modes you have higher energy, but you don't have a nice profile, or you can say the beam quality will not be good, or will not be suitable for certain kind of applications. Okay, these were the transverse modes. How we can control transverse mode? Simple, but in case of longitudinal mode, but in mode like have a spectrum or a single wave or single mode or something like this. This one, whether the length of that is necessary to generate a certain kind of output wavelength, or what frequency do we need, what wavelength laser do we need at the output of the cavity. So this one is calculated according to the length of the cavity. Remember, if you remember it. Now, definitely the possible way, if you see here the yellow portion here, reduce the length of the cavity, which is not practical actually. Okay, and why it's not practical, as I mentioned, that the length is calculated one. Okay, so if we reduce the length, everything will mess up and we will not get at the output what we really want. Okay, so what is supposed to be done to use a kind of, I don't know, these topics may be a little bit complicated for you people, but if you go through after my lecture, maybe you can understand. One, the word, or I can say there are two scientists actually, Fabry and Perret. So they actually designed a kind of etalon, two slides very close to each other. Okay, and it's a pair of reflective type surfaces. Okay, and very like the separation between them is very, very narrow, like this. And when the light pass through, enter, and it has a number of reflections. It has number of reflections, and then it can go out. Okay, so this kind of arrangement, we call it Fabry-Perret etalon. Okay, so what is supposed to be done inside the cavity? If you see on the right side of this diagram, this is your laser medium. Okay, this is the cavity. Okay, we cannot reduce the cavity length. So what we do, how we control the longitudinal boards, that we use a small etalon inside the cavity. Okay, so what it does, it only allows that modes, longitudinal modes, which satisfy the condition of constructive interference passing through this echelon. Okay. So this echelon is very, very thin. Thin in the sense the spacing between them is very small, micron, and it depends, it can be milli. So the only that mode will pass through which are interfering constructively inside this echelon. Okay. All the other modes which are interfering destructively will vanish somewhere. Okay. Extinguishes, and you get output the at least not all the modes, but few modes. Okay. So this is the solution. Rather to decrease the length of the cavity, to use any kind of echelon or two pieces of glasses, reflective surfaces, very close to each other, so that when the light pass through inside the cavity from this echelon, then only that mode will pass through who are having constructive interference when they pass through the echelon. Okay. And to understand more, like here, if you see, this is your gain, medium, gain. This is called gain cover, a gain curve, which is depends on the what kind of gain medium you are using. Okay. And these are the modes. Okay, the frequency modes. Okay, adjacent frequencies. Okay, like if let's suppose it's 530, 531, 532, 533, 534, 5, 6, 7, 8, 9, 10. These are the modes. Okay. So if we use echelon, okay, then only that modes will pass through which having a constructive interference. Okay. So rest of the modes will be vanishing somewhere or will not come out. Okay. So like this is the gain curve and all the longitudinal modes are there. We use the echelon. If we use the echelon, only two modes we assume can pass through. Okay, these two modes will look like this. Okay, so obvious all these modes is there inside the cavity, and the length of the cavity, it may be length of the cavity is like 10 centimeter or 5 centimeter or whatever. And if we reduce this by using the echelon, let's suppose we have 1 millimeter. Okay, so it means definitely not all the modes will pass through this echelon, but only few modes will pass through, and whoever interfere constructively, then that will be at the output of the cavity. So there is also Fabry-Perot interferometer exists, because whenever the waves or rays pass through, it interfere. Okay. So this is a specific example. I took it for the argon laser, because you know that the argon laser, it has a huge gain actually, and it can be tuned to different wavelengths. So we use the echelon, and this echelon can be rotated. So if you rotate, different modes can be tuned. Like if you go back here and here, this echelon, it can be rotated. Okay. So if it is rotated, then different modes, but limited modes will pass through. Okay. And this is how we control the longitudinal modes. Okay. So the longitudinal modes to control is a bit tricky, but it is needed in the laser, especially whose gain is huge, and we don't need all the wavelength at the output at all the times. Okay. Now, single frequency operation. Single frequency operation, it means we are using the, we are supposed to remove the longitudinal modes which we don't need it, which is, it's not, I mean, like laser has to be coherent, has to be monochromatic, and it has to be like a, the line spectrum at the output, the spectrum has to be very narrow, like single wavelength. It is assumed the single wavelength. So what we study here, that the single frequency operation or the single mode operation, we use this kind of thing, which is called Fabry-Perot etalon or simple etalon. Okay, and it has to be inside the cavity. Then we use prism. Why prism is used? To tune it. Okay, so prism is used so we can rotate the prism. You know that the prism is a dispersive element. Okay, it disperses the light when passed through. So we can, if we rotate this prism and to a certain angle, then a certain wavelength will pass through. Okay, if we rotate more, then other wavelengths will pass through. Not all the wavelength will pass through. Okay, it has to be at a certain angle. So the only that wavelength will oscillate in the cavity, which passes through that prism. Okay, and the etalon. Okay, so few words about the etalon here. It consists of a glass slide, it's quartz, and it's coated with some certain material. Okay, and slightly reflecting from inside, but not 100%. Okay, because on the other side, the light is supposed to come out. So etalon can also be acting as a interferometer. Okay, and it can resonate at certain wavelengths. It depends upon the dimension of the etalon, the thickness of the etalon. Okay. Here, to clear or to make you people to understand more, you can understand this is the whole gain medium and all the modes in the cavity. Okay, the cavity is 10 centimeter or maybe whatever, all these. And after use the etalon, when we use the etalon, definitely the separation between the two slides of the etalon is very, very small. So it's impossible that all the modes can pass through. Okay, only adjacent modes can pass through, and who can interfere with each other destructively or constructively. So then we have here these two modes here. After putting the etalon, we have two modes here, and the separation between the FSR, we knew it from the last lecture. Okay, and from these two axial modes or longitudinal modes, we get at the output like this. Okay, they may interfere with each other constructively, so we have one fringe here outside. Okay, and this is a single mode output. Okay, so what is the purpose of etalon? To eliminate the other unwanted the longitudinal modes or axial modes, unwanted frequencies. It has to be removed. So, and we can also rotate, if this is your etalon here, we can rotate it at certain angle to select the modes, which mode you want to select from here. Okay, but that is a long story. In simple, what we learned actually, these longitudinal modes, transverse modes, and how to control how to control these longitudinal modes and transverse modes. Longitudinal modes, as I mentioned that in case of ultrafast laser, we need these longitudinal modes. In case of a normal laser, we have to eliminate unnecessary modes. Transverse modes is always needed to remove to have a proficient or perfect beam. Okay, so perfect beam, to have a Gaussian like and round shape, nice beam, we need to have a 10-0-0 mode. And whether it's ultrafast laser or any kind of CW laser or any kind of laser, we need to remove or eliminate the other transverse modes in any case. 10-0-0 is standard mode. Okay. Other modes only, I mean, if you need very high energy, like in case of defense applications and the military applications, then you need very high energy. So in that case, modes doesn't matter. Okay. And longitudinal modes, keep remember, I'm summarizing you these people. So longitudinal mode, it depends on the length of the medium, laser medium or cavity, not the laser medium, cavity. And transverse mode, it depends on the dimensions. Okay, not only length, but the dimension, x-axis, y-axis, and etc. So the longitudinal modes, to control the longitudinal modes or axial modes, we can do like to reduce the length of the cavity, which is not practical actually, because if you remember, length is it has to be decided what output at the output of the cavity we need, what wavelength at the output of the cavity we need. Okay, so we cannot change the length after making these calculations. So what we do, we insert a very small piece of two glasses or slides, which is like very parallel to each other, and it's called Fabry-Perot etalon, and insert this one in the cavity so that only limited modes can pass through this etalon and suppress the other modes, which we don't need, longitudinal modes. And in case of a transverse mode, we use the aperture. Because it depends on the dimension, we can use the aperture, ring type aperture, so that the beam, and that aperture is supposed to be inside the cavity. So the beam passes through that cavity. And to have a nicer 10-0-0 mode, and rather to have 10-0-1-1-0, whatever it is, which is not needed. So in this way, these modes can be controlled. Now we move to the next topic here, the control of laser output. Control of laser output means, like I just showed you one setup, that it has a prism here. So that prism actually here is controlling the wavelength at the output. Okay, this is one of the examples how to control the output of the laser. To use a prism or like here, and to use the grating. With the grating, you can also control the wavelength, which wavelength at the output you want, or some other kind of devices which you see here, but you may not understand what is this. And here, these are devices which is it's also called the modulators, and it modulates the light when passed through it. So these devices are called electro-optic devices. Electro-optic devices. Okay. So if we go through here, many practical application actually, we need, for many practical application, we need a certain kind of laser output. It depends on the application. We may need a different wavelength, okay, and frequency, obviously, and so that we can have the output at the output of the cavity, the kind of laser we need at the output of the cavity to control it some way. So there are some devices like prism and grating. Okay, here this is your grating, this is a prism, and these devices are called passive devices. Okay, so why it is called passive devices? Because they have their fixed work. I mean, they only disperse the light. Okay, they disperse when the light passes through the prism, it disperses the light. Okay, and when the light fall or pass through any kind of diffraction grating, then the obviously it also disperses the light. Okay, so both of these passive devices are used to control the output, like what frequency or the wavelength do we need at the output for certain applications. Okay, and there are some devices which we call the active devices, active optical devices, and these active devices are, as I mentioned, that it's electro-optic devices. Okay, it has a certain arrangement, and when the light passes through, it modulates it. It uses certain kind of crystals inside and certain kind of technique, electric field, in some cases acoustic waves as well, and it can function in a different way. It depends how we use it. Has a controller with it. How do you want to modulate the light? How you can switch off the light passing through it and then release it in a very, very short interval of time, and these kind of things. Okay, so these are active devices and they can perform different kind of functions. It depends how we want to use it. And these devices are important when we look for the pulsed laser. So pulsed laser, whether it's by using the Q switching technique and other kind of technique. How many people know here what is Q switching? Salman?
Yes, sir. I know.
Gazanfar? This was the Gazanfar or Gazanfar?
Yes, sir.
Yes, sir.
No, one person, okay. Salman?
Okay, sir.
So what do you know about the Q switch? Do you remember?
Sir, by Q switching, we split the beams, and we by Q switching, we like if we use the laser of high power and we want to of high waves, and we want to split that in two parts, like 950, we split that to two parts, like 425, 425, or 550, like that.
No, Khasa, I think you forgot. Anyway, Gazanfar, do you remember?
Yes, sir. Sir, Q switching is actually the quality factor.
Mhm.
So first, if we first we have to build the intensity inside the cavity.
Mhm.
Then we dump the whole energy on go. So it
Okay.
gives us then the high power and the peak.
Yes, somehow you are right, actually. Anyway, let's move to the next here. Control of the laser output. So, as I mentioned, that the active, the passive devices like a prism and the grating you can see here in the diagram. So what it does here, this is a prism, and this is your laser medium, okay? And we can rotate this prism So we can have a different wavelength to oscillate in the cavity. So that if the lambda 1 is oscillating, then amplify lambda 1. If lambda 2 is oscillating, then lambda 2 will be amplifying in the cavity, and we get at the output lambda 2 from this side. Or it can be lambda 3, can be, it depends, I mean, how broader spectrum of the laser it has, I mean, without using prism, or you can say how broad the gain medium, the gain curve of this gain medium is. It depends. So we can just rotate this prism to certain angle, then we can have a different wavelength at the output. Okay, and this is simplest demonstration of controlling the laser output. Okay, and usually this kind of arrangement is used in argon ion laser. Other lasers, their gain curve is not very broad to have a number of wavelength at the output. So that is why it's for argon ion laser. And the next one here, grating. So whether to use the grating or whether to use the prism. Grating is more sophisticated and more expensive, more delicate. So you can see here that two possibilities. Whether to adjust the grating, this is a reflecting type. Okay, light is not passing through, but light is reflected. And what is the grating actually? I don't know how many people they know what is the grating actually. How many people know here that about the grating, the diffraction grating?
Sir, I know. Nargis Kapoor.
Yeah, sure.
Yes, sir. It's a piece of glass on which the lines are carved actually to the very precisely and very minimum, almost to the precision of the wavelength of light. It is used for diffraction purposes.
Yes.
There are infinite number of lines that you can't even count it with the naked eye. I don't remember it is more precisely to the wavelength of light.
Yeah, sure. You're right. So there are two kind of gratings actually, transmission type or reflecting type. Okay. The purpose is same, to disperse the light, and it's used different places, and it's very much common to use in ultrafast lasers. How we will study later on. So what we're doing here, actually, what these diagrams showing here, that this grating is tuned for a different wavelength. If you remember, this is the formula. Lambda is equal to 2d sine theta. Okay. So you to rotate the grating at certain angle, that is a theta angle, and then you can calculate the lambda. And what is the d here, Nargis?
It's the spacing between two lines, two slits.
Yes. So this is when you buy it, actually you get the specification of the grating, okay? Because this grating is a very sophisticated kind of optical element, and it's very, very expensive, the real one, especially the reflecting type. And to have a ruling on this one, it's really it's not an easy job. Anyway, we are using here to how to control it, how to control the laser output, and we can just rotate it. And according to this formula, we can find out which lambda at which angle we can get. So if we rotate, and then that wavelength will be amplified here inside the cavity, and we get at the output. Two possibilities: to use a mirror here, and other possibility to directly reflect from the grating. Okay. So in both the cases, we can rotate this grating to tune it for a certain wavelength, and using this formula. Okay, so these are the passive kind of optical elements, optical devices here. These are always used to disperse the light. Okay, so now generation of high power laser pulses. Okay, so controlling of the laser output is not finished yet actually, because this is, I just mentioned here, like passive devices or optical elements. But controlling of the laser is it's very vast subject, and it has many things. Even Q switching is also come in the same category. So how to generate the high power laser pulses? This is also controlling the laser, okay? So there are a number of techniques, not so many, few techniques. Like here, if you see that smash is the yellow one, the Q switching. Okay. The Q switching basically is used to have a giant pulses, large peak power, not the short pulses. Okay. Not very short pulses. Like very short pulses is a different thing. Here, in the case of Q switching, you may have nanosecond pulses. Probably in some cases may go to picosecond, even though maybe it's harder. So Q switching technique, basically it's used for to generate giant pulses or large peak power. Okay, and for a short interval of time. Short interval of time, like can be nanosecond. Okay, nanosecond and millisecond. It's obviously possible. Picosecond. Okay, and the picosecond, it's not very common, but nanosecond is very much common to using this Q switch technique. Other technique is use cavity dumping. It's very similar to the Q switching technique, but cavity dumping means that we don't use the partially polished mirror in the cavity. Both the sides are fully polished, and we extract the beam by some way. We'll see later what it is. And the third one here, this one is the mode locking. So mode locking, it gives you short pulses. Okay, and it generates the pulses in a very, very short interval of time, much shorter as compared to the Q switch. Much shorter means femtosecond. Okay, femtosecond pulses, the shortest. You can go to the attosecond, but not directly. And short pulse and very large peak power. Okay, so short pulse and very large. When the peak becomes shorter, the energy is concentrated in a very, very short interval of time. So that is why we get very large peak power. Okay, so like here, if you have a 30 femtosecond pulse, okay, you can easily get the peak power of terawatt. Okay, how that will be in the ultrafast lasers. Okay, so first what we study the Q switching, little bit about the cavity dumping maybe, and then mode locking will be all the way in the ultrafast laser actually. So mode locking term, it comes from the modes, longitudinal modes. Okay, so mode locking, lock the longitudinal modes. So we can have a broader spectrum. Broader the spectrum, shorter the pulse. Anyway, this is maybe may not understandable for you yet. Okay, so first thing to understand for the Q switching, the Q factor. What is this Q factor? It's a quality factor. Q is for quality. Basically, it measures the ability of a laser cavity to act as a resonator. And okay, so ability of laser cavity to act as a resonator, and the basic formula for this the Q factor is you can see the F naught, and F is a center frequency or the oscillation frequency, and energy stored of the mode, okay, and energy lost per second in a mode. Energy stored in a mode, and then energy lost per second in a mode, in a single mode. Okay. So quality factor, the Q value is depending on F0, which is the oscillating frequency, the central frequency, multiply with the stored energy of the mode and energy lost per second in a mode, one mode, okay? And probably it may not be easy for you to understand, but slowly, and move forward, maybe you can understand. The first point here, if you see, Q factor measure the ability of a laser cavity, and what are the laser cavity, and how much energy losses are in the cavity, how much energy losses. Okay, so it's to measure the energy losses in the resonant cavity, okay, in the form of a Q factor. So Q factor is basically the measure the ability. This is losses, and the gain in the cavity is basically the ability of the cavity. Okay. So, or in simple words, if you see here, mirror losses, measure of the mirror losses. There are always losses in the cavity, and Q factor is important. It helps us to understand these losses, okay, that ability of the laser cavity. And if you see this curve on the right side, what it shows, energy loss per second on the x-axis and the Q factor on the y-axis. Okay, so here, if you move on this side, it's very high losses. Okay, so Q factor value is very, if you see here, compare it like this, and here losses are low and Q value is high. Okay, and here Q value is low, so the losses are very high. Okay, so basically the losses in the cavity is utilized in the Q switching. Okay, we block the cavity from inside and it build up losses, and then we remove the blockage, then we get all the giant pulse at the output. Okay, the yellow portion at the down, if you see what it says, less the amount of energy dissipated, higher the quality factor of the resonator. If you see this equation, this Q is inversely proportional to the energy loss per second in a mode. Okay, so it's vice versa case. So energy lost, if the energy loss per second is greater, then the Q will be less. If the Q is greater than the energy loss per second will be higher. Okay, like here, low Q, high losses, high Q, low losses. Okay. Similar kind of equation here, and quality factor, similar kind of equation, just with the letters here. If E is energy, and this is energy of any chosen mode at time t. Okay, so this energy which is stored in a mode at the time t, and this energy will gradually dissipate with the passage of time. Okay, because of the losses, and so because of the losses, then it means the energy will be reduced. Okay, and reduction in the energy will be proportional to the stored energy. Okay, so here, if you see, where is my pen? Here. The reduction in energy will be proportional to the stored energy. Okay, and the interval of time dt. Okay, so this is a change in energy. Okay, and what it's saying, the reduction in energy will be proportional to the stored energy. Okay, it's a proportional. How it is proportional? Reduction in the energy will be proportional to the stored energy. So there is energy which is stored in a mode, and if this energy is reduced, and that will be how much energy stored, same energy will be reduced. Okay, with the passage of time. So it's a proportional kind of thing. And interval of time is dt, very, very short interval of time. So this equation will be building like this, and the negative sign comes because it's dissipate. Okay, it's reducing, it's losses. We are studying the losses. Okay, so on the right side, what we see here, this is time versus stored energy. Okay, so if we have Q, this Q and this Q, if the Q is equal to into 10 to power 4, you have this one, this curve, what it shows that the stored energy and the time of dissipation. Okay, so in case of red, it's pretty much goes straight away, and then it's straight, almost straight line towards the time. Okay, and in case of the green, it's a bit slanting here, and the behavior with the blue is pretty different kind of behavior. So okay, so what is this actually? Energy decay in a resonant cavity for different Q factors. Different Q factors. If the Q factor is 2 to 10, 5 to 3, 1 to 3. Okay, so what difference do you see? Energy decay. Here, energy decay kind of exponential, and here is also something like this. And here is very much abrupt from here to here, and then get almost zero actually. Okay, so this is what you see here. This is also quality factor. The left side, there is a formula which is Q is equal to F naught over delta F naught. F naught is a resonant frequency, and delta F naught is a line width. Okay, you can see here, this here. This is line width. So high Q value, at high Q, the red one, the high Q, you have narrow line width here. Then medium Q value here, quality factor. Okay, so medium Q value, you have the line width of green, and at low Q value, the line width is a blue one. So at low Q value, the line width is increased. So higher Q factor value, if you have narrow line width, which is needed. Okay, and in case of medium is in between the high and low. So this spectrum, it shows relation between the frequency or the wavelength on this side. Okay, and relative intensity or normalized intensity here. Okay, and it shows that the line width increases with the if the Q value is increases. Okay, so low Q value, the line width will be much narrower. On the right side, what you see here, This is also similar kind of equation, but here I'm using the sign proportionality. Okay, this is F naught actually is cutting from here. So here line width and here quality factor. So what is the effect on the line width of the quality factor? If the quality factor is here, the line width is inversely proportional. Okay, so inversely proportional is like okay, and Q is directly proportional to F naught. F naught is what? F naught is the central frequency, oscillating frequency, and delta F naught is it is like line width. Okay, so the Q factor is inversely proportional to the line width. Greater the Q value, so less will be the line width. Lower the Q value, high will be the line width. So this curve is showing the similar kind of things. Okay. Okay, so Q switching. What is Q switching here? This will be probably last slide today. Probably. Q switching, in simple word, I will try to explain in simple word. This cavity, you know that. You have a gain medium. You have cavity mirrors. Okay. And there is something in it. This switch, electro-optic switch can be, we call it Q switch. Okay. Here it shows that it's blocked, it's closed. On the other side, it shows that it is open. It's blocked, open. When it is blocked, pumping is going on. Okay, laser is not off, it's turned on everything. Pump is there. This is the gain medium. Population inversion is going on. Stimulated emission is going on. Okay, just we block the way the photons, the laser photons, to oscillate in the cavity. We block it, but it's building up. It's building up because pumping is not stopped. Okay, so we block it for a short interval of time, and then we open it. When we open it, we get huge peak power or giant pulse. First, we block for a short interval of time, and then we opened it, and we got huge pulse, huge peak power. Okay. When we open, what happened? The laser start oscillating. Okay, and we get the output. Here, the stimulated emission, the population inversion is building up. Laser is not stopped, but only the oscillation is stopped. So when abruptly oscillation is opened, we get huge, like bunch of photons, avalanche of photons, and we get the huge output. This is the explanation of Q switch in simple. And this Q switch here it depends. I mean, we can use a mechanical switch, but that will be, I mean, it cannot be very fast, obviously. So some kind of, in the commercial lasers, in the modern lasers, some kind of electro-optic switches are used. Electro-optic switches, they have a time to close for 1 microsecond, 1 millisecond, or whatever, and then open to get the joint pulse. So we get train of pulses after certain interval of time. It depends on the Q switch. And all these pulses, like here, 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 here. So these are the pulses of equal interval of time, huge peak power. Okay, but this technique is limited to the timing of the switch. So we cannot have very short laser pulses. Last slide. Evolution of a giant pulse, laser pulse through Q switching. Evolution, how it happens. Okay, this is, I drew it by myself, actually, these plots. Maybe if someone is very good in Python or something, it can be done. First, on the right side, what you see here, the losses and the time. This is the time, actually. Basically, time is important. This is the point where the losses, okay, maximum losses here. Begin with the high cavity losses. Okay, so begin with the high cavity losses when the switch is off. Switch is off, light is, the photons are not oscillating. Okay. Okay, so here population is going on, population inversion, pumping is going on. Here you can say in the beginning state, like when the laser even not turn it on. Okay. Here the laser is on, population inversion is there, and stimulated emission is there. Okay, but it's not oscillating because the cavity is blocked. This is the gain starting from here, and this is the time. This is the loss here. So this gain should overcome the losses here or become equal to, like here. This is the gain, overcome the losses. Losses are reduced here. Gain is now streamlined. Losses are reduced to zero almost. And at a certain point, we get a giant pulse at the output and all the gain becomes zero as well. All the energy is released. Okay. So this is how graphically we can show that at the beginning, when the laser is not even on, the losses are maximum. We don't have any output. Laser is turned on, the switch is off in the cavity. So the population inversion is there, but the switch is off, there is no oscillation. So it's built up, gain is getting higher, and when we turn off, turn on the switch, there's a confusion, turn off and turn on. Okay, close and open is much better to use for this kind of, not like conventional switch. Okay, so with the Q switching, much better to use a close and open. So here it's a close and here it's opened. When the switch is opened, gain is streamlined here, loss is reduced to zero, and we get a giant pulse at that. And after getting giant pulse, then the gain actually it's went to zero. Okay, so this is how the evolution of giant laser pulse through Q switch it happens. Okay, so that's all for the today. Q switching will be continue a bit, and then after that we will go to the mode locking. And mode locking means that we will move to the ultrafast. So this is how the things are happening, and I'm not sure whether you people understand 100% the things. Some of the students here, there's already very less students, but I suggest you people, I will upload, and you can go through and try to understand. Try to understand the thing actually that how it works and how it because QCT is the beginning point of the pulse lasers, and actually the modes are the beginning point to understand what is the lasers, pulse lasers are actually kind of. Okay, so if you have any question, you can ask. Otherwise, you can also ask in the next lecture. I mean, after reading, after going through it, there are some of things, and I assume that you will understand. Yes.
Okay. I have a question, sir. Sorry.
Mm-hmm.
Regarding to the Q switch,
Mm-hmm.
can you put the slide? It's one of the last slides.
Wait, just a minute. Which one?
Before?
Before. Okay.
Yes. In this case, the switch of the Q switch that is not the mirror, this center one, they do not produce population inversion. The population inversion is only in the cavity, right?
Population inversion is in the gain medium.
In the gain medium, sorry.
In the gain medium, yeah.
And we can
Yeah.
see like Q switching like analogy with an airplane when the turbines are getting at full speed and then put the brakes and then
Release. Yes, you are
release.
right.
Okay.
Yes, somehow it's similar kind of thing. Okay, so after that I have another actually meeting. So probably I mean Fatma Noor Bajwa and Nargis Ghafoor and Amna Saeed. If you have any question, probably you can ask in the next lecture. Okay, Ali Usman also, Zanfar, he doesn't need actually. Mauricio, do you have any questions?
Well, for example, time of these transitions in the game medium, and it has to be compared with the Q switching time, or
Yes, actually, somehow you are right, because we cannot have a Q switching for all kind of lasers, all kind of gain medium. So this time actually, I mean, in some cases you have to, like in case of Andy Yag is okay. So this is very much dependent on this thing. You're right, but I'm not discussing here this thing, because in this case you have to go to the energy level of all the laser the gain medium, etc. Not all the lasers can have a Q switching technique possible with it.
okay, thank you.
Yeah, welcome. Okay, guys. So let's meet in the next class. Oh, sorry. Yeah, next week, definitely next week. So I'm again encouraging you people to go through and have some questions. You can ask, not on the same day, but you can ask in the next lecture, because I assume that there are many things maybe you may not understand because of the background. Okay, so we'll see in the next class, and I hope you people will come with some kind of questions.
Yes, sir.
Okay. Okay.
Yes,
Okay
sir.
then.
Thank you, sir.
Okay. You're welcome.
Okay, sir. Allah Hafiz.
Allah Hafiz. Okay. Goodbye.